All right, guys, we're going to continue on with section 1.2, which is displaying quantitative data with graphs. So in section 1.1, we dealt with categorical data. Now we're shifting gears into quantitative data, so we're talking about things that can take on numerical values. So one of the simplest graphs to construct and interpret is a dot plot, something that you've probably seen in the past. So in a dot plot, each data value is shown as a dot above its location on a number line. How do you make a dot plot? Start by drawing a horizontal axis, a number line, and labeling it with a variable name. You want to make sure that you scale the axis from the minimum to the maximum value, and then mark a dot above the location on the horizontal axis corresponding to each data value. A couple things people forget to do when making a dot plot. They don't label or title the graph, so make sure that you always throw a title on that graph. If we're talking about the number of goals scored, that you're mentioning that we're talking about the number of goals scored. In addition, make sure that your scale is appropriate and that you're going up by the same amount each time. We have to go up by 2 each time, okay, in this particular example, or 1 or whatever you're doing. When you're making a graph, any type of graph, first thing you want to think about is you want to look at the graph and say to yourself, what do I see? What do I notice about the graph? So here on this particular graph, you might notice that the majority of the goals scored by the U.S. women's soccer team is from 0 to 5 goals. But then you also have these 2 outlier points here, which you want to make note of as well. Okay, so think to yourself, when you're looking at a graph initially, what do I see? What do I notice? So how do you actually examine the distribution of a quantitative graph? So when you're looking at the distribution of a quantitative variable, in any graph, look for the overall departure, and then for the overall pattern, and then for any striking departures from that pattern. Okay? So we saw that the majority of the goals scored were from 0 to 5, but then we saw those 2 kind of potential outlier points at 13 and 14 goals. So what do we do? How do we describe a distribution? Well, we use this acronym called SOCS, or SOC-V, okay, to describe that. And you'll hear me say, describe your SOCS, or use your SOCS all the time. Anytime you have a quantitative graph, SOCS is key, or SOC-V. So what does that stand for? The S stands for shape. So describing if there's any skewness or symmetry in the graph, if it's unimodal or bimodal, and we'll talk about what that means. The O stands for outliers, mentioning those 13 and 14 goals as potential outlier points. Anything that's unusual, meaning any gaps in the data you'd want to mention. The C stands for center. So talking about the mean, the median, where is the majority of the data located? The S or the V stands for spread or variability. That could be your range, or your interquartile range, or your standard deviation. And one of the most important things is to always describe the context. If we're talking about the number of goals scored by the U.S. women's soccer team, we better use that in our description of our data set or our distribution. You have to mention context. Context is crucial in everything that we do in our class. So note individual values that fall outside of the overall pattern. Those departures are what we call outliers. So make note of those outliers at 13 and 14 goals when you're describing the distribution. Don't forget your SOCS. SOCS, SOCS, SOCS. When you describe a distribution shape, there's 2 major things that we want to talk about first, and that's symmetry or skewness, okay? So you want to look, is the data set, the shape of the distribution, relatively symmetric, or is it skewed in any way? A distribution is approximately symmetric if the right and left sides of the graph are approximately mirror images of each other. So you can have a distribution that's unimodal, meaning it has one peak, which we'll talk about. This would be symmetric, but this would also be a symmetric distribution. A distribution is skewed right, or right skewed, if the right side of the graph is much longer than the left side of the graph. So it's always skewed in the direction of the tail. So wherever the tail is, that's the direction that it's skewed in, not where the hump is, and people get confused with that. We'll also take a look at our feet in class, and you'll notice that your right foot is skewed to the right, and your left foot is skewed to the left. So if you think about your foot, here's what your foot looks like, maybe. You'll notice that your right foot is skewed right, and your left foot is skewed left. Looking at these graphs, okay, our first graph is approximately symmetric. It's not perfectly symmetric, but you're looking at the general overall pattern. Your middle graph is skewed left, the tail is on the left-hand side, and your siblings graph is skewed to the right. One of the most interesting statistics questions, and something that you always see on the AP exam, is when we're asked to compare two or more groups. When you're asked to compare two distributions, you're still using your SOCs or your SOC V. You want to discuss the shape, the center, the spread, and any possible outliers. Okay? We're going to do this example in class, but one important thing to keep note of and to write down is that you want to use comparative language. So what does that mean? We want to use things like higher, lower, less, more. You don't just want to say the mean household size in South Africa is 12. The mean household size in the UK is 8. That's not comparing. We need to use things like higher, lower, more, less, and things like that to actually compare the distributions. We'll answer this question in class as well. Another type of graph that you can see that you've probably seen in the past is a stem plot, or also called a stem and leaf plot. Stem plots give us a quick picture of the distribution while including the actual numerical values. So in a dot plot, we can't tell exactly what the numerical value is sometimes, especially if it's something like a decimal or a fraction. But in a stem and leaf plot, we can see that exact numerical value. When we're making a stem plot or stem and leaf plot, we want to separate each observation into a stem, which is all but the final digit, and a leaf, which is the final digit. So if we look here, we have 132. And we want to change that 132 into a stem and leaf plot. The 13 would be my stem, and the 2, which is my final digit, would be my leaf, and I get something that looks like this right here. You write all possible stems from the smallest to largest in a vertical column, and draw a vertical line to the right of the column. Each leaf is in the row to the right of its stem, and you want to arrange the leaves in increasing order out from the stem. One important thing people forget to do is to include a key whenever you're making a stem and leaf plot. So what does 13 with our line and 2 represent? Maybe it represents a weight of 132 pounds. And you want to make sure that you include that. We'll take a look at a stem and leaf plot in class and go through this example. One possible thing, and again, we'll look at this in class with an example that you can do, is when the data values are bunched up, you can get a better picture of the distribution by splitting stems. What does that mean? It means instead of having just, say, 3 stems of 1, 2, and 3, we're going to split our stems and basically create a low 1 and a high 1. And we'll go through an example in class of this as well. Two distributions of the same quantitative variable can be compared using a back-to-back stem plot. We'll go through this example, but it's just basically combining 2 stem plots into one and comparing them that way. We'll also discuss unimodal, bimodal, and uniform distributions in class as well. These dot plots, you can try to answer on your own, and we'll go through the answers in class. Final type of graph that we can use for quantitative variables is called a histogram. In a histogram, it looks very similar to a bar graph, except the bars touch, and a histogram is used for quantitative data. So right here we have a frequency table discussing the percentage of residents from each state who were born outside of the US. And they've created it and created the frequency table for us with the number of states that fall into each of these categories. On the right-hand side, you see the histogram that matches this set of data. So your y-axis will be your frequency, and it's important to label these, and then your x-axis is the percent of residents born outside the US. Notice that these are what's called my bin widths. okay? And I've just created the histogram that matches this data set. You can see that the bars touch here. We could also use our SOX or our SOC V to describe this distribution. A couple things to think about. Don't confuse histograms and bar charts. Histograms are used for quantitative data, and bar charts are used for categorical data. In histograms, the bars touch, and we could use SOX or SOC V to describe them. In bar charts, we're dealing with categorical data, such as the eye color that people have. And you would not use SOX or SOC V to describe them, and the bars do not touch. Use percents instead of counts on the vertical axis when comparing distributions with different numbers of observations. This is what's called a relative frequency histogram. Remember, percentages are always better to use when we're making a comparison. Just because a graph looks nice is not necessarily a meaningful display of data. Remember that. There's one more set of data here dealing with the MBA teams. We'll go through this and create the histogram in class. That's all for section 1.2, guys. Good luck, and I'll see you in class.